One of the many applications of rigid body mechanics, like we've been doing, rotational Newton's second law, is skeletal biomechanics. And you can calculate important things about muscles and bones and joints using the approach of rigid body kinetics, rigid body dynamics. And so I just want to do a couple of examples to show like what kind of calculations you can do using these approaches. I'm going to simplify this a little bit. So for one thing, I'm always going to assume that one of the limbs connected to the joint we're considering is fixed. Things get, philosophically, there's no real fundamental difference between all your limbs moving together and just one limb moving. But we've only been focusing on rigid body motions where a body is fixed at a single pin, and so that's the way we have to approach this. We're also going to simplify this by just calculating isometric motions. So, well, not motions at all. We're going to assume things are still, and we're just going to calculate forces. This actually, in a lot of body movements, you can make this approximation and still get good calculations even when the body is moving. So we can get good results using this approach that I'm going to give you right now. So I'm going to do two examples, one in the elbow, one in the ankle. So first I'll do one at the elbow, and we're going to treat the elbow like this. So there's the forearm, and we're going to treat the elbow joint like a pin, and the upper arm as a rigid body. We're going to assume that this is fixed. So really the only thing that allows motion is the forearm. And we're going to say that the hand is holding a mass of 5 kilograms. And in order to hold this ball like this, you can imagine if this pin was just free to rotate and there were no muscles, it wouldn't be able to hold it in this position. So what we have is a bicep muscle that goes like this. And we are going to assume that the distance from the insertion of the bicep, the more distal part of the bicep down here on the forearm, is 0.015 meters from the elbow joint. And we're going to assume that the distance from the elbow joint to where the mass is located is 0.5 meters. And the origin of the bicep muscle is far enough up the bone that we can get good approximations by just treating this as vertical. It's not going to change anything very much. And then we're just going to treat this muscle the way you treat all muscles always, as just cables that can only provide tension. And so what we want to do here is calculate how much tension is there in the bicep. And I'm going to approximate the mass of the forearm and hand as 1 kilogram. And let's do this calculation. Okay, so I'm going to start with a free body diagram. And we have to choose what body to isolate. I'm going to isolate the forearm. So I'll just think of it as a sort of a stick like this. And now let's start thinking about what forces are acting. There's a contact force from the 5 kilogram mass. If that's not moving at all, there has to be, I mean, we could do this calculation, but I'm going to just sort of shorthand through this. But in order to hold up a ball that's 49 kilograms without any acceleration, you need to apply an upward force to the ball of 49 newtons, 5 kilograms times 9.81. And that means that there's a downward force of 49 newtons applied by the mass to the hand. Okay, so that's one force. And then we have the weight of the forearm and the hand. I'll put it right in the middle. We're treating this like a rectangle. So that's going to be 9.8. Then at the elbow, we'll do this exactly like we always do pins. So we'll have an Rx and an Ry. And then the last thing is that muscle tension. Remember, we're treating this as vertical, just as an approximation. The rule for a cable tension is parallel to the cable, away from the body. And we'll give that the tension T, and then that's everything. A lot of times before I do the free body diagram, I'll calculate the moment of inertia of the body. In this case, though, since we're assuming that this is at rest, there's no angular acceleration. I doesn't matter, because whatever it is, you're going to be multiplying it by 0 for this angular acceleration. So let's start calculating these moments. The about point is the elbow, the pin. And so, like always, the moment produced by R is 0. Then the cable tension, that's plus or minus the force, times the perpendicular distance from the pin to the force. So this is 0.015. Now, if this is free to rotate about the elbow, which way would this force make the forearm rotate? It would be counterclockwise. So we want the positive. So this is 0.015 T. Now we'll go to the weight force. That's plus or minus a force of 9.8 newtons and a distance from the elbow to the force of 0.25 meters. That weight force would make this rotate clockwise, so we want the negative. And this is negative 2.45 Newton meters. And then the last thing we get to is that 49 newtons. So that's plus or minus a force of 49, a distance of 0.5. That force would make this rotate clockwise. So we want the negative, and that is negative 24.50 Newton meters. And now we can set this up in the rotational version of Newton's second law. We're just adding up all these moments. So we have 0.015 t minus 2.45 minus 24.50 is equal to the moment of inertia times the angular acceleration, but we're assuming that this arm is at rest, so this is going to be 0. And now we have an equation that lets us solve for t. So 0.015 t is equal to positive 26.95. Divide both sides by 0.015, and you get that the tension in the bicep is 1,796.67 newtons. So it's interesting to note here that because of the leverage of the different things going on, it doesn't take 49 newtons to support a 49 newton weight. You know, it doesn't take a 49 newton tension in the bicep. It takes a really big tension in the bicep in order to support that weight. And that kind of thing is stuff you can use for, there are a lot of applications. If you're trying to deal with injuries and you're trying to rehab injuries, you can figure out motions that are getting you the right amount of muscle force for your rehab, for example. There are pre-surgical decisions made based on calculations like this. Simulations are done using this kind of thing that you use then in, you know, video games and also research projects. So let's do a similar calculation now with the ankle. Again, we're going to assume that the angular acceleration of everything is 0. And this is sort of a famous biomechanics example that gives you sort of a surprising result. So we are going to assume that a person is standing on a ledge on their toes like this. And this is the ankle joint. This is the point on the heel where the Achilles tendon connects. And then this is the point of the foot that's in contact with the ledge. And I'll give some distances that we're going to use. Let's say this distance is 0.04 meters. That's 4 centimeters. And let's say this distance is 14 centimeters. And then we'll say that the height difference between these two is 5 centimeters. It turns out it's not going to matter what the height difference is from the contact force on the ledge to the ankle, just because of the line of action of that force. And so let's say that the mass of everything except the foot is 70 kilograms. 70 kilograms. And the foot mass is 0.4 kilograms. And we want to calculate two things. First, we want to calculate the tension in the Achilles tendon. And second, we want to this time calculate the contact force in the ankle. So what we're going to calculate is the force applied to the foot by the tibia, or by the, the shank of the leg, the calf part of the leg. Okay, so we are going to approach this the same as we did last time. Again, we're going to assume that alpha is equal to 0, and that means that the moment of inertia doesn't matter, so we don't have to calculate that. And then I'm going to do a free body diagram of the foot. I'm just going to draw the foot as a rectangle. And the forces, so here is the ankle. Down here is where the Achilles tendon connects to the heel. Here is the center of this rectangle, and that's where I'm going to apply the weight force. And then this is where the foot makes contact with the ledge. And we have enough information to know all those distances. So first, I'm going to assume, again, since the Achilles tendon is roughly vertical, in order to simplify this calculation, I'm going to assume that this is an upward force T. At the ankle, we have what we usually have, an Rx and an Ry force. Then we have the weight force of 0.4 times 9.8, so this is 3.92 newtons. And then we have the contact force from the ground. Really, we should calculate this, but it wouldn't be too hard to calculate this, and I'm just going to skip that step, that this is just the weight of the person. It has to be if the person's not accelerating. And so this has a mass of 70 plus 0.4 times 9.8, so this is a force of 689.92. So there it is. We have, let me try to make this one a little more clear. So we have the cable tension, the contact force, the weight force of the foot, and the contact force from the ground. And we're going to, first of all, calculate what that T is. So one by one, I'm going to calculate all these torques. The one for the cable tension is plus or minus. If you move this cable force up along its line of action until that line between the hinge and the force location is perpendicular to the force, you can see that that is a force of T, a distance D of 0.04. And that force would make this rotate. If this foot is free to rotate around that hinge, that T force would make it rotate clockwise, and so that's negative. And so we have negative 0.04 T for the moment produced by the Achilles tendon, or the torque produced by the Achilles tendon. Then we'll go to the contact force. So this, as always, produces 0 moment. Then the weight force of the foot. The distance from, let's see, the distance from the distance from the heel to where the foot makes contact with the ground is 18 centimeters, 0.18 meters. But that's all the way to the heel. We want to remove 4 centimeters of that because we just want the distance from the weight of the foot, where the weight is, the center of this rectangle, the horizontal distance to the ankle joint. So we're gonna take 0.09 and subtract 0.04, and so we get 3.92 for the force, 0.05 for the distance. That would make this rotate clockwise. So we have negative, and that is negative 0.196 Newton meters. Now the last one is that 689 force. So we have plus or minus a force of 689.92. The horizontal distance from the ankle to this floor force is 0.14 meters. The reason we want the horizontal distance is we would have to move this floor force along its line of action up to the top of this rectangle so that the line from the hinge to the force is perpendicular to the force. This would make it rotate counterclockwise, so we want the positive, and so this is 96.59. And now we can use the rotational version of Newton's second law. We have negative 0.04 t minus 0.196 plus 96.59 is equal to I times 0, so this is just going to be 0 because there's no angular acceleration. And so what we get here is 0.04 t is equal to 96.394. And now we can calculate that t, divide both sides by 0.04, and you get that the cable tension for the Achilles tendon is 2,409.85 newtons. So again, to support the body weight, you don't have to have a cable tension, a tendon tension of the body weight. You have to have one that's much bigger because of the geometry. And you can figure all that out using rotational Newton's second law. So now we're going to take the next step on this one, and we're going to use this to calculate the contact force in the ankle. And this is a famous example because you get this surprising result that we're going to see that the force that is applied by the upper leg to the foot at the ankle is much bigger, much bigger than the weight of the person. So in order to calculate the contact force, we have to use Newton's second law, regular Newton's second law. And so I'm going to go back to this free body diagram and put these things in. So we only have one horizontal force, so Rx times I, and then I'll lump all the vertical forces together. We have a positive T, a positive Ry, a negative 3.92, and a positive 689.92, and this is in the J direction. And all of this in Newton's second law is equal to mass times acceleration. Well, again, this is just going to be 0 because there's no acceleration. And so we have to set the x parts equal to 0 and the y parts equal to 0. The x parts are easy. That just tells us that Rx is equal to 0. that's not surprising because everything is happening vertically. Then we go to the J equation. This is the I part of the equation. So now we'll go to the J part. And it says T minus Ry. Oh, and we know what T is, so I'm going to put that in here. We just figured this out. And so the J equation says 2409.85 plus Ry minus 3.92 plus 689.92 is equal to 0. And we have everything except Ry, so we can calculate that. And you get that Ry is equal to 3,095.85 newtons. How big is that compared to the weight of the person? The ankle force that has to be supported is over 4 times body weight. And so again, knowing this kind of thing can be useful for rehab. You don't want to, if you're trying to rehab a hurt ankle, you don't want to get into body configurations where you're asking for these huge contact forces to be supported or muscle forces to be required. And so this calculation is useful again for medical applications, rehab applications, simulations that you can use for research or video games or whatever.